So earlier we talked about a set of really important functions that we're going to be using throughout our journey in mathematics, and we refer to those as the toolkit functions. I think it'd be a good idea to run through the toolkit functions and quickly identify their domains and ranges. So one of the early toolkit functions we talk about is the constant function f of x equals c. And remember, with our function notation, this f of x is playing the same role as y. So what does the graph of our constant toolkit function look like? Well, it depends on the value of c, but this is going to be like the graph of y equals some constant value. And remember, that always gives us a horizontal line if c is positive. If c is positive, that horizontal line will be above the x-axis, and if c is negative, then that horizontal line will be below the x-axis. So let's, just for the sake of getting a picture on the board, let's assume that our constant here is a positive value for c. And so since we can go as far to the left as we could ever possibly want, and same thing as far to the right as we could ever possibly want, our domain is all x values or all real numbers. So in our inequality notation, that'll look like this. X is between negative infinity and positive infinity, or negative infinity is strictly less than x is strictly less than positive infinity. If we want to use interval notation, that would look like the open interval on both sides from negative infinity to positive infinity. And also, we have a special name or a special letter to indicate this set of all real numbers, and that's that uppercase Blackboard R. So everything in the real numbers is in the domain of our toolkit function, the constant function f of x equals c. But what about the range? Remember, the range is all the y values our graph hits. And remember, we're fixing our constant c, so that's not going to vary as x does. So we're only going to get one output or one constant out of this function. So our range is just going to be a single y value, that single y value of c. All right, so the next toolkit function I want us to graph and find the domain and range for is our identity function, or f of x equals x or y equals x. And right, we should recognize that this is just a linear function with a slope of 1 and a y-intercept of 0. And so the graph of this function is just going to be that straight line going through the origin, pretend that goes through the origin, and cutting the first and third quadrant perfectly in half. All right, so from the graph of this toolkit function, we can see that, well, the domain, or all the x values, as well as the range, or all the y values, are going to be all real numbers. We can get any negative y or x value we want by moving to the left on the graph. And on the other side, if we move farther to the right, we can get any positive x or y value that we could possibly want. Just real quick, remember the domain here, as well as the range, are the set of all real numbers. And if we wanted to, we could write that in inequality or interval notation. But we got a lot more toolkit functions to go through, so let's keep on moving. Okay, so the next function in our toolkit is our quadratic function, y equals x squared, or f of x equals x squared. And that gives us that shape that we should know by now as the parabola. All right, so looking at the graph of y equals x squared, we can notice for the x values, we can get any negative or positive x value we could possibly want just by moving sufficiently far enough to the left or to the right. So our domain is once again going to be the set of all real numbers, or the interval from negative infinity to positive infinity. But what about the range? Well, remember, the range is the set of all outputs or y values. And now we can notice on the graph of y equals x squared, we have no y values that are strictly below 0. The smallest y value we obtain, and therefore the smallest y value in our range, is going to be y equals 0. Y has to be greater than or equal to 0, and then it can go up from there as far as we could possibly want to go. So we can describe that within an inequality as y is greater than or equal to 0 and less than positive infinity. Or also as an inequality, we could just say that y is greater than or equal to 0, not including an upper bound, implies that we're going all the way up to positive infinity. And then of course we could use our interval notation for this as well. it would be closed on the left because we can include that lowest y value of 0. Right? Just plug in x equals 0 to get that y value out. But we can't include that endpoint on the right of infinity. Remember, infinity is not really a number. It's just telling us we can get as big positive or negative as we want. All right, so the next toolkit function in our list that we want to find the domain and range of is our cubic toolkit function f of x or y equals x cubed. And so this toolkit function has that popular S-type curve to it. We'll talk about some different ways to describe this curvature in a later section, but for now we're just interested in the domain and the range, and what we can notice is both the domain and the range of this function are going to be all real numbers. All right, so up next we have our toolkit function f of x equals 1 over x, also known as the reciprocal function. And this one's a little bit more interesting than some of our earlier toolkit function examples because we have our first discontinuity in one of our toolkit functions. From the graph of our toolkit function 1 over x, we can see that we have this discontinuity at x equals 0, and we have a vertical asymptote here at x equals 0, and we also have an interesting horizontal asymptote at y equals 0 for this function. Both of these are going to have to be taken into account when we describe the domain and range of this toolkit function. So if we scan all the coordinate points that end up on the graph of 1 over x, remember the domain is the set of all x values we can obtain. If we go far enough to the left, we can get any negative x value we want. Go far enough to the right, we can get any positive x value we want. There's actually only one x value we cannot obtain on the graph of 1 over x, and that's when x is equal to 0 because, well, we can't divide by 0. And so our domain for this function are going to be all those x values that are strictly bigger than negative infinity but less than 0, or we could have those x values that are bigger than 0 and less than positive infinity. So this is one way to represent our domain using that inequality notation, although I think there's a couple much simpler ways to describe this domain, even still using our inequality notation. Remember, we don't really need to include those lower or upper bounds in each of these individual statements since they are already implied, meaning that we can simplify our description of the domain here using inequality notation by just saying x is less than 0 or x is greater than 0. But even that is still kind of cumbersome, and I think there's an even quicker way to describe this, although technically it's not using an inequality, it's using an inequation. Just say x cannot be equal to 0, right? That's the most concise way to describe the domain of 1 over x. So what about the range of 1 over x? Well, it's actually a very similar conversation. We can get any positive y value we want just by moving closer and closer to x equals 0 on the right-hand side. We can get any large negative number we want by moving closer to x equals 0 on the left-hand side. The only y value we have trouble hitting is the y value of 0 due to this horizontal asymptote. So again, the quickest way, most efficient way to describe the range here is just to say that y cannot be equal to 0, or we could write out these longer statements like we had for x, but just replace that x with y instead. All right, so let's keep the show rolling. Up next is our 1 over x squared or reciprocal squared toolkit function. Let's see if we remember what the graph of this toolkit function looks like. Remember, we want to have all these graphs dedicated to memory. So the function 1 over x squared has a lot of the same or similar properties as the previous toolkit function we just looked at, 1 over x. We have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. The big difference is because we have x squared in the denominator, we can never obtain a negative output or negative y value on the graph of this function. So here we have the graph of 1 over x squared. Let's go ahead and look at those x values to describe the domain and the y values for the range. So when it comes to x values, it looks like we can go as far to the left as we want and start, or go all the way to negative infinity, and then we can move to the right without any issues until we get to that vertical asymptote at x equals 0. Once we're over or past that, we have no issues any longer, and we can get all those other x values to the right of 0. So our domain, let's go ahead and maybe use interval notation here, is going to be the interval from negative infinity to 0 in union with the interval from 0 to positive infinity. Again, just kind of a wordy way of saying x cannot be equal to 0. But we want to know how to use all these different notations. All right, so we've successfully described the domain of 1 over x squared. To finish this off, let's go ahead and describe the range, or the set of all y values or outputs that our function obtains. So we don't actually have a lowest or minimum y value on the graph of this function, but we can get really, really close as we could possibly desire to that y value of 0 that corresponds to this horizontal asymptote. So our range is going to start at 0, but not actually include 0 because we cannot obtain that y value. But then we can go as far up or increase as much as we want. So our range is going to go all the way to positive infinity. So here we have the domain and the range of our reciprocal squared function using interval notation. All right, so the next toolkit function in our list is f of x equals the square root of x, or y equals the square root of x, or y equals x to the power of 1/2. And remember, the graph of the square root function is basically just half of a parabola twisted on its side. So it's going to look something like this. And from the graph of our square root function, we can very quickly identify the domain and the range. And what we see here is that they are exactly the same. And so remember, our domain is just the set of all x values our graph obtains. So we start at x equals 0, and we can go as far to the right as we want. So if we're using interval notation to describe our domain, we can start at 0 and go as far to the right as desired. So that'll look like the interval from 0 to infinity with a square bracket on the left and a open or parentheses on the right. So like I mentioned earlier, the range is exactly the same. So the y values tell us the range. Our lowest y value is 0, and we can actually obtain that y value. So we include the y value of 0 in our range. That's what that square bracket indicates. And we can go as far up in the y direction as we want, as long as we move far enough to the right. So the domain and range of our square root function are all values greater than or equal to 0. So after the square root of x, we look at the cube root of x, which is the same as x to the power of 1/3. And so if we carefully reproduce the graph of our cube root function, or x to the power of 1/3, should end up looking something a bit like this. The shape should look familiar. It's just the same shape that our cubic function has, although it's been flipped around and transformed a little bit. Later on, we're going to talk about how the cube root function is really just the inverse function of the cubic function, and we'll see how the domain and range of a function and its inverse are also related. That's a conversation for another video. For this video, we just want to look at the graph of our cube root function and identify the domain and range, or all the x and y values our graph obtains. But what happens for this function is what we've seen for a few of our other toolkit functions. We can hit any x or y value that is out there, so both our domain and our range are going to be the set of all real numbers, or the intervals from negative infinity to positive infinity. All right, so the last function we got to discuss at the very bottom of our toolkit is f of x equals the absolute value of x. So remember, the graph of f of x equals the absolute value of x is really just two straight lines put together to create this flying V type shape. So here we have the graph of our last toolkit function, y equals the absolute value of x. And we can also see that any x value is represented by at least one point on this graph. So our domain, or the set of all x values, is all real numbers, or the open interval from negative infinity to positive infinity, but our range does not match our domain in this example. Our range is all the y values, and here we can't have any negative y values, right? The absolute value function has to spit out positive numbers, and those outputs are our y values, so they must also be positive numbers, but we can't actually hit 0. So if we're using interval notation, that'll be the interval from 0 to positive infinity, where we have a square bracket on the left because we include y equals 0. And if we wanted to use inequality notation, the simplest way to describe it would just say y is greater than or equal to 0. So earlier I talked about some of the uses of finding the domain and range of a function, and our absolute value function actually brings up another really important use of knowing the domain of a function, and that's when it comes to these piecewise defined functions. So here we have our absolute value function, but it can actually be defined as a piecewise function where it's x if x is greater than or equal to 0, and it's negative x if x is less than 0. So that first part of our domain, x is greater than or equal to 0, is describing this first piece of our piecewise function using that first formula. And for the rest of our domain, when x is less than 0 or negative, we use the formula for the other piece. And that's y equals negative x, which is also a straight line, but with a negative slope instead. So we'll be working with these piecewise functions every so often in precalculus as well as calculus. And it's very important to distinguish which pieces of the piecewise function we are using for a particular moment. And it's going to depend on what part of the domain we are on.